In this video, we will take a look at another application of linear systems. Now, this application is very specific in nature, and there's a specific process. So unlike the more general story problems where they each are a little bit different, this particular application has a certain consistency about it. And so the application it's called polynomial. Don't we love polynomials? Interpolation. All right. So I will give a description of the problem that we're trying to solve, and then give just a little taste of the theory that's associated with it, and then see how that theory is used, how it's actually used, right? So here is the setup. Given n distinct, or we could say unique, ordered pairs, so what does that mean? So you have like a x1, y1, and then an x2, y2, and so on. You have then xn, yn as your nth ordered pair. So you have these ordered pairs, and distinct means that you've taken out all the duplicates. So you're not going to have, like 1, 2, and 1, 2 again. They're all going to be different ordered pairs, right? And so that's what we're given. Now, before I tell you what we want to do with them, one of the first things you learn to do with ordered pairs is how to plot them. So again, just for simplicity and so that my plot doesn't get too complicated, I'm just going to assume that the ordered pairs are like in the first and second quadrants. So they might be here, 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 and just dot, 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 right? So, and so I just, so we have these ordered pairs, we plot them in our XY plane, and what we would like to do now, kind of based on this pattern, it looks like these points might form like some kind of polynomial pattern. So what we would like to be able to find is a polynomial that passes through each of these ordered pairs, right? Right. So we want this to be a polynomial. So we want a function y equals f of x, where f of x is a polynomial. Right. And in a second, we're going to add an extra requirement to it that will make it so that we will always get a solution. In fact, we will always get a unique solution, right? Add that in a second. So given n distinct ordered pairs, dot, 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 the polynomial, right? So the polynomial passing through these n ordered pairs, so passing through these n ordered pairs is called an interpolating polynomial. So to interpolate in this sense, in a mathematical sense, is to pass through. So interpolating polynomial. Now we're using a polynomial. This process can be extended to other types of functions. You can interpolate with trigonometric functions, which is a big thing. But right now we're only using polynomials. Now, what do we know about polynomials? Well, we know their particular form. You know, you have powers of x, and then you multiply by coefficients, and then you add those terms together. You know, so the nth degree polynomial tends to look like this. A constant term, and then a constant times an x, and then a constant times x squared. And then, you know, the nth degree polynomial will go up to, so it'll be a sub n times x to the n, right? And so this is, so if the coefficient of x to the n, so if a sub n is not equal to 0, we say the polynomial has degree n, right? So we say p sub n has degree n. Okay. Well, the thing about just saying a polynomial is the degree is arbitrary. Like it could be anything. So maybe, you know, we could find several different polynomials that would pass through these n points, right? Which means, you know, we wouldn't have a unique answer to this problem, like if we just kind of left the degree open. But if we want a specific degree, like the polynomial of least degree, then it turns out we can like with that added constraint, we can guarantee having a unique solution. So let's see if we could figure out what is the special degree that would work for certain cases, and then we would just make a general statement. So this is not a result that I'm going to prove. It's an interesting proof if you ever come across it. But let's see what we could do. So let's say we start with n equals 2, meaning we have two ordered pairs. Right? Two ordered pairs, I'm sorry, yeah, if we have two ordered pairs, then we know we can fit a line through it, right? If I just have one ordered pair, I can't even fit a unique line because I could have it with all these different slopes. But if I have 2 points, then the polynomial, the unique polynomial, would have to be linear, right? So if n is equal to 2, then this implies that the unique polynomial would have to be linear, right? There's only one line that passes through 2 given points, right? So the unique polynomial must be linear. And what does that imply? That implies that the degree would be 1. Remember, a linear function, a linear polynomial, has degree 1. All right. So again, so what I'm going to do is just kind of illustrate the pattern between the number of given ordered pairs and what degree will guarantee something unique, right? Well, if I have 3 distinct points now, right? And again, let's say these 3 points, they don't all form, they're not collinear, so they don't lie on the same line, right? Because if they do, then you just end up with a linear function. But let's say the 3 points are like this now. So n equals 3. Then think about it. If I want to fit a unique polynomial through these 3 points, it would have to be a quadratic, because if I allow the degree to be higher, then what that means is I can have with the larger degree, thinking back to algebra, you have more and more turning points, or you have more and more min and relative max points. So you could use you could use several higher degree polynomials if you want to fit just 3 points. But if I want the polynomial to be unique, it would have to be a quadratic. So it would have to look, something like this, right? Again, so in this case, the unique polynomial must be quadratic. And this is kind of so now, and again, remember what it means for a quadratic, its degree is 2. So in general, notice the pattern between the number of given points and what degree we should use in order to guarantee a unique polynomial. That degree happens to be 1 less than the number of points. So if you start with 2 points, to guarantee a unique polynomial, it has to be degree 1. If you're given 3 points, then to guarantee a unique polynomial, the degree has to be 2. So in general, just given n data points, so in general, and this is the little bit of theory. This is the little bit of theory that again, I won't give the general proof. It's beyond the scope of this course. But intuitively, if you think about it, starting with the linear case and just kind of progress through higher degrees, you'll see at least why intuitively it should happen, and it does. So in general, given n distinct ordered pairs, the unique interpolating polynomial, sometimes called optimal polynomial. So the unique interpolating or sometimes called optimal, like optimal because it's the best you can achieve while still having like one and only one thing with that property. So the unique interpolating or optimal polynomial must have degree n minus 1, right? So optimal polynomial must have degree n minus 1. All right. Now, so let's look at an example, right? So the question is, so now we know what type of polynomial it would have to be so that we would get a unique answer. The question is, how do we find it? And what do these problems look like? So let's take a look at an example here. And I'm just going to give the ordered pairs, and let's do one with 3. So let's say it passes through -1, 2, and 1, -4, and 2, 4, right? And then, so that's the given thing. So we're going to say find, so our instructions would read something like find the optimal polynomial that interpolates these points. Find the optimal interpolating polynomial. Okay, so that's our goal. So we know since 3 ordered pairs are given, right? Since n equals 3, the polynomial must be quadratic. Right? That's what we just established. The polynomial is a quadratic. Now, the next part of it is where you will see some variations depending on what you're reading or watching. So for instance, we know the general polynomial tends to be written like this. Your y equals ax squared plus bx plus c, where a is non-zero. Earlier on when I wrote down the polynomial, I wrote it down like this. And this is kind of a notation that comes from Calc 2 with Taylor polynomials. But I wrote it, instead of writing it in decreasing powers of x, I wrote it in increasing powers. And instead of using ABC, since at that point I didn't know the degree, so now if I put a 2 here, but still use that earlier form that I used, it would be a sub 0 plus a sub 1x and then plus a sub 2x squared. If you remember like your Taylor polynomials and Taylor series, they were typically written in increasing powers of x. Ultimately, it doesn't matter which general form you choose, whether you want to use the more commonly used form, or if you want to use this other form that again mimics like the way we write down our Taylor polynomials. So either one, you pick a general form, and then we're going to use one of those general forms. And the goal is to figure out what the coefficients of that polynomial have to be in order for the polynomial to pass through all the given points, right? So let's use the easier form, if you will, or maybe easier is not the right word, but maybe the more familiar form. So we're going to use that form. Now, how do we turn this problem into a linear system, right? Well, the thing about your ordered pairs is this. You remember, it's a pair that consists of an x value and a y value. So, for instance, starting with -1, -2. This is, again, in words, and this is how I even write it out sometimes, like when I'm using the ordered pair notation and concept. When x is equal to -1, y is equal to -2. So if I plug into my general formula for the quadratic, if I plug x equals -1 in, so do this, right? Then that would have to give me a y value of -2. So I'd plug the -2 there in for y. And then if I simplify this, so -1 squared is 1, so I'll have a minus b plus c equals -2. Hey, that looks like a linear equation to me with variables a, b, c, and I can see my coefficients. So that's one equation. So then if I repeat this process for the remaining ordered pairs, I'm going to get, and because the ordered pairs are distinct, what's guaranteed is that the equation is never going to be repeated, right? That's the whole idea of having distinct points. So you're not going to have the information from any given point be duplicated, right? So yeah, so let's do that and write down the other one. So the second ordered pair, 1, -4, plug 1 in for x, and -4 in for y, and that one simplifies just as easily, so it looks like this, and then plus c, that's -4. So here's my second equation in the system. So this will be a plus b plus c equals -4, right? And then finally, using the third ordered pair, 2, 4, plug 2 in for x, and 4 in for y. So we're going to have a times 2 squared plus b times 2 plus c. That's equal to 4. So the third equation that we need in this system is 4a plus 2b plus c is equal to 4, right? So let's write that system down in, so let me put it all together now. So here we go, -2, and then a plus b plus c equals -4, and then 4a plus 2b plus c is equal to 4. So then what we can do is solve this. Now we've looked at basically two methods for solving. We can do Gaussian elimination and put it in one of our echelon, let's say a row echelon form, and then do back substitution. Or we could use Gauss-Jordan and go all the way to the reduced row form. Either way, I'm going to start by putting this system in augmented form. So like this, -2, and then 1, 1, 1, -4, and then 4, 2, 1, 4. So there's our augmented system, right? And what's nice is the way it's set up, we have our pivot of 1. So now let's go through our elimination. So I am going to do this operation first. So I'm basically going to wrap my work around. So I'm going to start it here. So I'm going to take negative row 1 added to row 2, and then -4 row 1 added to row 3. When I do that, I get this equivalent augmented system that looks like this. So I'll have a 0 there, I'll have a 2 there. Look, I'll have a 0 there as well. And then I'll have a -2 there. So the negative of -2 is 2, plus -4 is -2. And then do something similar, using that pivot to eliminate the positive 4. So -4 plus 4 is 0, and then 4 plus 2 is 6, and then -4 plus 1 is -3, and then 8 plus 4, that's 12, right? And if we simply, so now this is going to be our pivot, and if I multiply the second row by 1/2, so if I take 1/2 times row 2, then I'll have a pivot there, and then I can easily eliminate the 6 below. So it looks like the elimination is going pretty well. And once we get it in the echelon form, we can decide if we want to take it further to the reduced echelon form. But I'm thinking, I mean, I can start to see the solution right away, right? And then you'll have the 0, and then 6, and then -3 and 12. All right. So so now let me circle my pivot, my leading 1. And we're going to do -6 row 2 plus row 3, right? So multiply row 2 by -6 and then add it to the row below. Let me write out the other entries. Tell you you're solving linear system and you're just doing a lot of bookkeeping, a lot of arithmetic. So then we'll have 0, 0. This is still -3. Here, and then we will have positive 18, because you'll have -6 times -1, that's a positive 6, plus 12, that's a positive 18. Now I'm going to take -1/3 times row 3 to make that a leading 1. So -1/3 times row 3. And I think at this point we can see the solution quite easily. So we have 0, 0, 1, and then -6. And then the other two rows above remain the same. And then 1, -1, 1, -2. All right. Now, so remember what we're solving for A, B, and C, and we have them written in that order. So the first column corresponds to the variable A, the second to B, and then the third to C. So this bottom equation is telling me that C is equal to -6. Perfect. The middle equation is telling me that B is equal to -1, right? Now we still have because this system is in REF. It's not in RREF because here are two pivots and we have non-zero entries above them. But because we had, so much of it ended up being reduced anyway, we can just write down the top equation, use our back substitution, and solve for A. If you wanted to formally go ahead and do the Gaussian, Gauss-Jordan elimination, you could, but I think seeing that the first equation is relatively simple and we already know B and C, just use the back substitution. It might eliminate any potential for error. So we have A plus 1 minus 6 is equal to -2. So A minus 5 is equal to -2. So A is equal to 3. Now what do we write down? What is our answer? Remember our original goal, and it's a while ago, but the original goal is to find the interpolating polynomial, which is the ax squared. This was the form we settled on. So once we know A, B, and C, our final answer is this. The polynomial, the unique polynomial that interpolates those 3 points, ordered pairs, is 3x squared minus x minus 6. And that's our answer, right? So it's not just that we found A, B, C as these numerical values, but it's the fact now we replace the kind of the placeholders in our general quadratic with the constants that we just found. And then we could use this the way we've used all sorts of polynomials in terms of finding roots. We can find derivatives, we can find other values of y that the polynomial passes through if we happen to know the x values, right? So that's polynomial interpolation. It relies on a little bit of theory, which I gave you the intuition for, but the process of converting it to a linear system and solving is pretty straightforward as long as you work through the problem carefully. So hopefully you found that interesting, and if you did, well, stay tuned and for another application that you might find just as interesting. See you then.